I will turn it over to Ophir.
Thank you very much. So thank you, guys. And I know it's the last talk of the day, so again, thanks for coming. I'm Ophir, and today we're going to talk about detecting process injection using network data. So before I start, I'll introduce myself. So if you guys have been to the last talk here of Or's, he introduced himself pretty well, and I too work for Akamai. So Akamai is a big corporate that specializes in cybersecurity, and specifically in Akamai, I work for the Hunt team. So before that, I was a research team leader in the military. I did that for 6 years in a defensive unit, and for the last 2, I've been working for Akamai. So we in the Hunt team, we hunt for threats, and we're basically an additional service over the Akamai microsegmentation platform, also known as the Akamai Guardicore platform. So if we're going to talk about process injection, let's talk about why process injection. Why does this thing even exist from the first place? So process injection is basically an attack technique that is stealthy, it's reliable, and it's been working well for threat actors over the years to hide their payload, either if it's from EDR solutions, antivirus solutions back in the day, or just from security analysts. So let's talk a little bit about the history of process injection. So right when Windows came out, with Windows NT, we were introduced to the create remote thread DLL injection, and also to the AIT hooking. After that, in the mid-2000s, we were introduced to more injection techniques, one of them being the SSTT hooking. And after that, we're introduced to process hollowing, also known as RunPE, and APCQ, which were first used in the late 2000s. After that, DLL reflective injection came out, and also in 2016, we were introduced to atom bombing in Black Hat EU, and doppelganging came out, which is another injection technique, and right after that, in the Elastic group, we're introduced to process ghosting, which we all know from dating apps. So we're defenders, right? We're security researchers. We don't care about abusing these injection techniques. So let's talk about detecting them. We'll start with this example of the create more thread injection technique. And here, when an attacker uses this technique, he basically loads a malicious DLL from disk using the create remote thread or the antivariant API call, and basically takes his DLL and loads it to a specific process that he has permissions to. So what we can do is iterate over the legitimate process and look for an illegitimate DLL. And another one is the AIT hooking, which in this one, in order to make it happen, an attacker takes a legit process which imports legitimate DLLs and changes the addresses of DLLs of these functions to point to illegitimate code. So again, if we go over the process and the imports of that process, we need to make sure those addresses point to the correct locations. And the third one we're going to talk about is process hollowing, also known as RunPE, like we said, where here the attacker brings up a legitimate process, a real legitimate one, but swaps the code inside with illegitimate code. So he brings up a legitimate process. It could be from System32 or any other place that he wants to, and swaps the insides of it with his own process. And in order to detect it, we basically look for discrepancies between the so-called legitimate process, which is the outside of the process, and the code that the attacker inserted, which is the illegitimate code, which resides inside. Two of these are detectable using Sysmon. So if you have Sysmon deployed in your network, you'll find it is event ID 8 for create more thread and 25 for the process hollowing. So basically, if we want to take a broader look at the detection of them, we can see that there are main things that are similar in each of these detection methods. So there are two things we need. Either the ability to trace API calls or direct access to our memory. If it's kernel memory or user mode memory, but basically we need one of these two things, preferably both. So this is something we rely on when we detect these injection techniques. And the second drawback is that EDR bypasses are everywhere. When an attacker takes control of a host, if it compromises a server or an endpoint, the first thing you will check is what antivirus solution it has installed on it, right? If it's this EDR or that EDR. And the second thing you will need is to understand how he bypasses it. So we, as threat hunters, cannot always rely on the fact that the EDR will detect that injection technique. And think of it. Sometimes, as a threat hunters, we will have hundreds of customers, and each customer will have another kind of a security solution. So you cannot take for granted that the solution will stop the injection, or you cannot even take for granted that your customer will even have an EDR or a security solution. And the most important thing about our detection is that network packets don't lie. So what do I mean by that? Many host-based artifacts can be bypassed or changed or manipulated, but if you're an attacker and you're making communication, you will certainly have to take into consideration that the network might be monitored, and the network is much harder to mess with. So what would an attacker do? Let's say I'm an attacker and I successfully injected payload into a process. Okay, cool. So what can I do with it? So maybe I can communicate to a CNC server. I can send home a message. I successfully compromised this asset or that server. Maybe I want to deploy reverse shell to maintain persistency. Maybe I will start crypto mining because it will help my wallet get bigger. Or maybe I want to scan the network to see what other hosts exist in it. Maybe I want to continue my lateral movement attempts. Or I can do whatever I need. So again, this is all dependent on what the attacker wishes to do. So how can we, security researchers, analysts, threat hunters, detect all of this malicious or possibly malicious activity? So let's talk about detection. But before that, let's talk a little bit about my job. So in Akamai, the good thing is we have a lot of data. Lots and lots of data from hundreds of customers around the world, but not only basic 5-tuple data or firewall logs or anything like that. We have process-level deep data, meaning we can know for each communication which process initiated that communication and also which process received the communication. So we basically have all the fields we need to know about each communication session. So what we can do with it? Think that we have month and month of this communication data from so many networks. We can basically learn how each process behaves, and then when the process behaves differently or in an anomalous way, we can catch it doing anomalous things and start investigating. So how does a process communicate? Well, that's a hard question, because each process communicates differently, and the interesting is that even though we might see the same identical processes in different networks, those same processes might be still communicating differently when they're deployed in different networks. So I know it's a little bit small, so let's zoom in on an example here. We can see that, let's take the second line. So in the Postgres process, even though you say, okay, it's a Postgres process, so how many ports should it be using? 2, 5, 15? So from our data, we can see that it generally uses more than 1,000 different destination ports for outgoing communication. Same for the other two. So they use many ports while communicating in the network. So how can we use this data that, as you understand, that varies a lot to catch those processes when they communicate in an anomalous way? So in our research, we saw that even though some processes might be using many destination ports, if we classify them to something we call port groups, we can note that even though they're using many ports, they're generally using the same kind of applications that are tied to those ports. So to understand it better, we can look at some examples. The Docker proxy process uses 61 different destination ports, which is not a small number. But if we look at what kinds of ports it uses, we can see that it generally uses high ports, so those long list of ports, and the RPC port of 135. And that's it. So it might be using many ports, but not so many applications. So by using these port groups, so-called, we can give better context to the detection algorithm and better understand how each process communicates. So we took the whole port range and classified each port into some port group. As you can see, I gave here some examples. So the DHCP translates to these 4. If we see a process using one of these 4 ports, we can say, it's using DHCP. And the full port classifications is present on the Akamai blog. You can surely enter it later. And while developing this method, we had many, many questions rise up. So the first one being, okay, I already bragged about how much data Akamai has, but how much data is enough to assume a process communication? Do we need a gigabyte of data? Do we need 100 sessions? And we can say, okay, we know how this process behaves. Maybe we need amount of data from more than one network. Maybe we need data from 100, 10, 2, I don't know. Another question is, okay, so processes do not always behave the same. So if we see a process behaving in a certain way in one network, does that mean it will behave the same in all others? Maybe it's an anomaly that should be checked. Maybe we should take it for granted. Okay, so it behaved like that, and we should take it and insert it into our baseline. Also, should all anomalies be treated the same? So what do I mean by that? Let's say we have a process that communicates in SSH. We've seen it in 100 networks, and every time it uses the SSH protocol. One time, out of the blue, in a new customer, it suddenly used port 50,000. So let's say a high port. Is it interesting? Maybe. Is it an anomaly? Yes. But is it interesting? Is it more interesting if we saw the same process suddenly use RDP? So both are kind of the same anomaly, but here it's using different ports. And the most important thing is, can we hunt for anomalies in every process? Maybe some processes are more stable than others. Maybe some are random. Maybe there are processes that it doesn't matter what it will do. It will be very hard for us to find it doing anomalous communications. So in order to answer that last question, we took the processes that we have data about and classified them into specific groups. So we try to measure if a process is consistent and it's easy to detect anomalies in, or maybe it's inconsistent and it's random and it will be very hard seeing when it does something malicious. So the first group would be the stable group. So that's pretty straightforward. It means the process behaves the same in all of the networks we're monitoring. And the unstable group means the exact opposite. So for every network we're monitoring, it behaves completely differently, which will be random and harder to look for anomalies. So if we stay with these two groups, we will not be achieving too much, because not all processes obviously go into one or the other. There's still more stuff to be filled in the middle. So we came up with this third group, which is the semi-stable group. This means that the process behaves the same, but only in the range of ports that is the non-high ports range, meaning from 1 to 49,000, the process behaves the same. So for each of the processes in this group, we completely ignore the ports in the high ports range and just focus on these ones. And applying the same logic, we came up with these three groups that are based on the Nmap top ports parameter. So Nmap maintains a list of the most common ports that is known in the wild. Meaning if you're a pen tester and you want to scan a specific host, but you don't want to be too noisy, you can just use the top ports parameter and specify how many ports you want to use. So if you want to scan the 50 most popular ports, just specify 50. So we use this classification by Nmap to basically classify each port, just like in the semi-stable group, by that specific group of ports. So let's take an example. If we see a process communicate randomly, but inside the Nmap top 12 group, it will communicate the same in all networks, we can say, okay, this process is Nmap top 12 stable. Okay, so let's say we classified all of the ports into these classifications, and now all processes I meant, so each process has its own category. So is this methodology any good? Well, it has its cons and pros, so we'll start with the pros. First, I don't know if you saw that, but that last line means that we're monitoring only processes that we saw in 3 or more customer networks. So like I said, we have hundreds of customers, and for each of the processes, we will take it only if we've seen it in 3 or more, which means it's a popular process, and it will surely make us have enough data about it. So with that number of networks means we have enough data about the process. We have sufficient data, meaning we have at least, enough of the amount of data, and also we have variation. Because each process, like we said, behave a bit differently in each network, we have a good variation because we saw it in at least 3. And it also helps us because let's say we have an incident about a specific process. Now we have 3 customer networks that we can compare it to. So it also aids investigation. And the second thing is that the number of communication sessions won't affect the judgment of the detection algorithm. So that's a weird sentence, but what it means is that if we saw a specific process, let's say one process is deployed in a customer and suddenly that customer has a spike, and we see that this process receives lots of communication, but it still uses the same port. So why would we take into account the number of sessions that it initiates? So we don't want to do that, and by looking at a process per customer, it helps us avoid noise. And of course, this method has cons as well. So unfortunately, most processes do not appear in at least 3 customers. Most of them could appear in 1 or 2, and with this, we will be missing them, as they will not go into our learning algorithm and into the baseline. So, we could have hundreds of customers, but still, if, let's say, a specific application is only installed in 1 or 2, even if it's deployed all over the customer network, we will still not monitor them, which is sad. And the second thing is, we talked about the use of port groups. So let's say we know now that the process uses these 2 port groups. Which one does it use more? Maybe it uses this more often than this. Maybe it used this port group once, and it will be interesting for us if it used it again. So we're not keeping this information, we're not tracking it. And this is the second con of this methodology. So with this, we moved on to a new way to study these processes. And we used the support and confidence measurements taken from the world of data mining. Support, meaning the amount of data we have about the process. Do we see it often? Do we see it sometimes? How many times have we seen it? And the second thing is the confidence, which measures the relationship between 2 items in the data. So if a process uses a specific port group, does it use it often or less often? We will see an example soon. So let's take a look at some simple example. So for support, let's say we're a shop, we're a grocery store, and we have a data set of transactions. So out of the 1,000 transactions we have, 300 of them are of apples. So the support of apples in our data is going to be obviously 300 divided by 1,000, which is 0.3. And regarding confidence, so if out of these exactly the same 300 apples, half of them are red, then the confidence of apples towards red apples is going to be 1/2. So 150 divided by 300, so 50%. Okay, so how does it look like in our data? We're not we're researchers. We don't care about apples and, we care about these processes. So I gave an example here. We can see that the SQL.exe process has the support of 0.003, doesn't matter, and it uses 3 port groups. So SQL, high port, and other. And the confidence of each one is written there. So it's easy to see that this process uses SQL more often than the others. And another thing to note, that if before we were looking only at how a process behaves in a customer, now we have another kind of measurement. So our data point would be of host, a process, and the port group. So what does that mean? That instead of only looking at a network, we would look at the number of hosts in the network. Because before, remember when I said, let's say we have a customer with a process deployed all over it, it's a lot of data and we will lose it. So here we take into consideration the number of hosts that we've seen the process run on. Okay, so how will the detection logic look like? We learned how a process behaves. We can compare it to new data. And we're going to use a sliding window baseline in order to achieve that. So, as you can see here, what's happening is that we take all of our new data and we compare it to the history of the process. In this example, we take the data of today, so all of the communication, all of the process communication that's happening today, and we compare it to our baseline, which consists of, in this example, it's a month of data. It could be more, it could be less, depends on your data retention. And after we compare the new data to the old data and alert about the anomalies, the date shifts, and the data of today will be used for the baseline of tomorrow. So tomorrow's communication is going to be compared for today and the rest of the history. So let's take a look at some code, because our detection doesn't look like this. It looks more like real code. And we will take a look at this sample SQL code in order to explain it better. So, as you can see, in this subquery, we take all the connections that have happened today. So these are the new connections. And you can see that we take each destination port, and like we did before, we classified it into a specific port group. Okay, so we have the communication of today. And now we select the baseline. So we select each process, the relevant support, which port groups we've seen it use, and then we have the confidence for the relevant port group as well. And you can see some interesting condition here at the bottom, that we take only processes with specific support. So here the support comes into play, meaning we only want to take processes that we have enough data about. So how does that affect our logic and our detection? So higher support means we will have less processes in the baseline, but we will have more data about these processes, which will generate more reliable incidents. The incidents will be more based, as each incident will be based on, more data. Though it has the drawback of less processes in the baseline, so we might be missing some of the processes if we used a lower support threshold. And after that, we're going to compare the new communication that we receive to the old communication. So here you can see that we select our baseline and we join the communications, the new communications of today on process. So we use a join here and not a left join. So basically, if we have a new process that does not appear in the baseline, then we have nothing to do with it, right? So we only want to compare processes that we know how they communicate. And then you can see in the condition that we want to select all port groups that have not been seen before. Okay, so we have that. But if you remember, we asked a question before about what if we've seen a process communicate in some sort of way, and we still want to see it again when it happens. Because I gave the examples that out of 100 networks, we see it in 1, but it could have been initiating only one session, and it is still anomalous, and if it happens again, we will want to know. So here the confidence comes into play. So these are just sample numbers, but what that means is that either it's a new port group that have never been seen before, or we've seen that port group before, but we've seen it so little that it's still interesting for us if it pops again. So this is the second condition. Okay, so like all detection algorithms, we have our false positives. And before we talk about how we deal with these false positives, let's talk about what kinds of false positives we might have. So from our experience, there are a couple of false positives that could occur with this detection method. So there could be proxy servers deployed in the customer network, which will make some processes communicate in another way. Also, think of an IT admin that suddenly switches the software from working with IP addresses to host names. Okay, for him it's nothing. The software still works, he's happy, he goes home. But what does that mean for us? It means the process suddenly communicated in the DNS protocol. It suddenly started sending out DNS requests, which if we haven't seen that before, it might appear as an anomaly. Also, domain authentication could cause various packets of different protocols to get generated. Sometimes the software manufacturer will release a new version that communicates just a little differently. Or maybe it has a network-wide configuration, and we will see an example of one of these false positives that corresponds to that type. So here, we have an example of some process that we've only seen it communicate in these two ports. So you can see port 80 and port 443. And suddenly, one day, it started communicating using port 1111. Have any of you seen that port before? So it's a weird port. And if we look at the history of how this process communicates, we can see that generally speaking, it uses 443, 80, and contacts various kinds of destination domains. You can also see how many times it contacts each. And down below, you can see the anomaly that we have three logs of the process using the specific port to a specific IP address, so we don't even have the destination domain. So we kept looking, and we had a conversation with the customer, and like I said, this is a false positive. So at the end, what we found is that that specific port was just a port that was configured so processes could communicate to the internet gateway in that specific network. So yeah, sometimes you'll investigate some anomaly and it will be a false positive, but it's still interesting to see them and learn from the so-called mistakes and then fix your detection. Okay, so what can we do about these false positives? So there are two things that we can do. The first one is check if this behavior is used in that specific network. So if we've seen other processes using the same port, and we've seen other hosts, so not just one PC, we've seen other hosts communicate the same way, and we've also seen the same kind of communication happen for a long time, we can know, okay, maybe it's an anomaly, but we've seen this happen before, so it's probably not worth wasting our time on. Maybe we should investigate more interesting incidents. And the second thing is that we can learn from past incidents and maintain a specific allow list for either specific processes or specific customers or networks, and generally try not to face the same incident twice as long as it's a false positive. Okay, so all of this would be for nothing if it wouldn't detect any real attack, right? Because we're not just writing detections to have fun. We need to detect the bad guys. So I'm going to present you how this method detected an actual injection. So it started out with us onboarding a new hunt customer and running this detection method. And what we found is 5 processes which deviated out of the respective baseline. So as you can see, you might even recognize some of these processes because they're running on basically any Windows machine. And they started communicating to large parts of the network using the SMB protocol. And they were all legitimate processes with injected payload. And you can see a screenshot from VirusTotal. And this corresponds to one of these processes. And it's truly legit. And the image from disk is clean. And the interesting is that you will not find them in the history and in the baseline using SMB. So they're all using other protocols, but they never, ever used SMB before. So we have an anomaly here. And how does it really look like? So this is a screenshot from the Akamai microsegmentation platform. And as you can see, we found this behavior on 3 total hosts. On one of them, it looked like this. So a specific host suddenly communicating on SMB to other parts of the network. And on the right-hand side, you can see one of these processes communicating from the system user to other hosts on SMB. Okay, so after we had this incident, we started investigating. We looked at scheduled tasks and services and files and commands run and communication. And we looked for communication that was not seen before and found these 2. So on the bottom, you can see this svc-host executable running from this weird directory, communicating to some IP on SMB. And the second thing is that you can see HTTPS communication to some unknown domain. And so it's running from system32, and the process is named DLL host X, which might trigger something in your mind, but processes are generally not named this. This actually masquerades the DLL host.exe that actually really exists in system32. So this is just to evade detection by some security analyst and to look legitimate. So we find these on 2 hosts, and we kept looking. And as you can see, these 2 executables are known to the cyber community and flagged as malicious on VirusTotal. So the DLL host X is a crypto miner, and the SVC host is an Eternal Blue scanner. Okay, Eternal Blue 445, interesting. So after we kept investigating, we found the calling script. So let's go over the script quickly. And we can see that it first writes some string into some exe file and copies itself to another directory. And I'm going to speak like this script is actually running these commands, but what it's really doing is just preparing some bat file that it will run later. So after that, it echoes some asterisks to eb.txt. And we found that this actually, what is eb.txt? So this is a reference to the Eternal Blue vulnerability. So the script here basically marks which vulnerability was used to affect and infect that host. And after that, it decides to tunnel DNS communication to Cloudflare public DNS server, and it receives communication on these 3 high ports using Netch, and communicates those requests to 1111. After that, it makes sure that a PowerShell scripting language exists and runs some more, runs a PowerShell command to fetch some malicious PowerShell code. And so this is the actually decoded, this is base64, so this is the decoded payload. We can see that it contacts some CNC servers and runs additional payload that it downloads. And what does this payload do? It does 3 things. So it collects information about the host, host name, IP addresses, MAC addresses, things like this, and sends them to the attacker. It also downloads a Monero crypto miner and runs it via a scheduled task. So it's persistent even if the host decides to restart. After that, it does a couple of more things. So it makes sure that the task scheduler service is running, and then it deploys some scheduled tasks. It uses the same name for the scheduled task with different executables. It creates, it deletes, it runs. Here, as you can see, it downloads using the MSHTA executable. It downloads some additional JavaScript payload to run on the host, and then runs some other scheduled tasks. And at the end, it looks, it also starts a service that was installed beforehand remotely. And the last thing it does there is just make sure that no more than 10 CMDs are running. This is probably just to make sure that it is not stuck in a loop of deployment. It then deletes the username, the administrative username that the attacker created. You see the payload is running. There's no need for a backdoor user. And at the end, it runs the script, runs another executable, and deletes itself. So if you followed along, at the end, we have one of these scheduled tasks still deployed, and we also have the scheduled task deployed from the PowerShell encoded command. OK, so as you can see, these domains are malicious. And they're registered. This is just some of them, but they're registered to the same organization. And you can see in that script there are a lot of IOCs that we can leverage in order to detect more affected hosts and find all of the places the attacker reached. So as you can see, just by communication, on the right you can see a couple of hosts listening on this exact port the attacker specified. So here we can find more affected host, and on the left-hand side we can see communication to Cloudflare's DNS service. So using these communication methods that the attacker used, we can find the rest of the infection. And just before I touch on the next things that we did, I'll just talk about OSQuery for a second. So if your guys are not familiar with OSQuery, OSQuery is an open source agent that is developed by Facebook. It has been developed for a couple of years now, and what it does is let you ask questions about your hosts. So it has an SQL-like, you can ask questions like in SQL form, and you can query many, many tables regarding scheduled tasks, services, files, hashes, and many other things. And fortunately for us, we have it already integrated into the microsegmentation platform. So using OSQuery and OSQuery capabilities, we could take these IOCs and look for them in the network. So as you can see, you might recognize some of these files from before. We're looking for the malicious files the attacker deployed. We're looking for the username that it used. We already know that it uses the Eternal Blue vulnerability, which is crazy how it's still working, but it used the Eternal Blue vulnerability to deploy itself on other hosts in the same network. So we want to know if there are more hosts that maybe have not been affected but are vulnerable to Eternal Blue. And we also looked for scheduled tasks, also the malicious service that it used, and more. So even though the attacker used randomly generated names, generally speaking, the behavior could be compared to other attacks that it did, and we can contribute all of the activity to the WannaMine attack group, also known as BP. So this attack group is a crypto mining group, and this threat actor has been active since 2018 and still active to this day. So even though he hasn't changed his tactics too much and using a vulnerability that was once supposed to be at least patched in 2017, it's still working for it, and it has been active for what? It's like 6 years already. Okay, so we talked about detecting anomalies in outgoing communication. We have the process data. We know how it communicates. We can find when it communicates in an anomalous way. But you guys might be asking, okay, so if we have that data already, what about incoming communication? Because we know what processes are listening on what ports. So from our research, we found a couple of things. First, most malicious communication is outgoing communication. The attacker compromises a specific server or endpoint, and it will generally want to either report back to base or keep moving, or generally speaking, just generate outgoing communication. And also, listening ports are easily configurable, meaning that how a process behaves, what ports it listens on, generally an IT guy who wants to deploy some software, the software will let him choose the ports that the application uses, otherwise it might break. So this really makes our anomaly detection harder when we go and look at listening ports, which means incoming communication. But even though I just tried to convince you it might work differently, I can still say that it works and it reveals interesting communication about the network in general. So if a specific application is deployed and it's deployed using a specific port that was never seen before, it's still interesting for the network admins to know, oh, maybe we have a new path of communication that we didn't know about. So even though it might not be malicious, it could still be risky for the network security in general. Okay, so what are we going to do next? So first, we're going to release the actual communication baseline that we have. So it will be out in the upcoming days. And it will contain all the information that I talked about. So the process, the support, the confidence of the specific port groups, and the destination ports that we know how each process communicates. And I can say that this logic, and this is the second point, the logic can be implemented using other data sets. So just like a process is tied to a port or a port group, we have other kinds of data that we can say the same about. So like a service that is tied to an executable. And I can say that we already implemented this kind of logic for services as well, meaning we want to find known services that are suddenly running malicious executables. So executables that are running from other directory or another executable name or anything like that. And another thing we can do is add more features to the detection. So we could work with other fields like destination domain or ASN, or maybe some processes only communicate internally. And then when they communicate on the same port but externally to internet, we can know that it's not supposed to happen. And yeah, I encourage you to try it. Try it using your own network data. So like I said, we're going to release the data set, but if you prefer to use your own network data to build a baseline, you can do that. It might be even more relevant as the data will be based only on your network. Maybe you can combine both. It could be really interesting. Many EDRs or firewall logs can contain process data. And also you can use, this is a screenshot from Sysmon, so you can use Sysmon Event ID 3, which has all that information that you need to do some similar detection. Okay, so any questions? Okay, thank you for listening.
All right, this is it for the day, folks. There is happy hour in 15 minutes down there.